Well, want to welcome everybody for joining us today, and thank you for using the PCB circuit design application of preference being Eagle. In today's webinar, we're going to be talking about BGA routing. My name is Edwin Robledo. I'm part of the support team, and with me today is Jorge.
Yeah, my name is George Garcia. I'm a product support specialist for Autodesk Eagle here in the States.
Excellent. So today the topic is about BGA fanouts. BGA is maybe one of the most complex systems used on a board, a chip, and it's quite complicated. And Eagle has fully integrated a BGA router, which is basically dedicated to that. In the meantime, I'm going to be switching over to our presentation page where Jorge will be sharing his screen. Now, throughout the presentation, go ahead and use the chat box that you see there. It should be appearing on the bottom right corner of your page. Just go ahead and use that box there to post any questions that you have throughout the presentation. We will allow a Q&A session towards the end as well. That way you can ask questions if you want to just leave them for the end. So with no further delay, I'll let Jorge take over and of this interesting topic. So have fun. Thank you for joining us.
Okay, guys, so hopefully everyone can see my screen. Please confirm if you can. Okay, good. So as I was mentioning, the goal of today's webinar is to talk about BGA routing. It is, as time has moved on, become a very common and popular package choice just because you can cram a lot of functionality into a very small space. So almost all mobile phones use these types of packages. Their main downside is they're not easy to experiment with at home. They do require some sort of reflow capacity, so either an oven, or I've heard of some people doing it with hot air guns, although that's hit or miss. But as you can see, really the difficulty stems that there's no easy way to get an iron to the balls of the BGA. Okay, so in addition to that difficulty, from the point of view of laying them out, because they're so densely packed and we have so many pins in a small area, they're very difficult to route. So usually what will happen is that you will fan out. In other words, you will break out all of the pads that you need to connect to the outside edge of the BGA, and then from there you can route to other parts of the design. So as you can see here, we have a basic board, and in the middle we have a BGA. Okay, the letters BGA stand for ball grid array, and they represent that on the underside of the package you'll see there's these little balls of solder. Hence ball, they're on a grid, and they're an array. Pretty self-explanatory. Now, how do we fan out, or how do we get even these inside signals, the ones deep within near the center of the BGA? How do we fan these things out? How do we break out all of these pads so that there's an easy way to connect to them? So that's actually a very deep subject. Entire books have been written about the algorithms used to fan out BGAs. There are also lower bounds on the number of layers minimum that you need to be able to fan out a certain type of BGA or a certain number of connection points. So there's a lot of theory behind it. But before we go into that, what we're going to do is talk about what are the main ways or the main facilities you need to have to be able to fan out a BGA. So let's first go to the DRC. And we want to talk about the vias. Okay, as you know, in Eagle we have blind and buried vias. Blind vias are vias that start on a surface layer but don't exit out the other end. Hence, they're blind because they can't see through to the other side of the board. Buried vias are vias that are created internal to the board. They're not visible from either end, from either surface layer. So, as you can imagine, producing these features is very expensive. So you need to really consider whether you need blind or buried vias. Almost always when BGAs are involved, unless it's a very small BGA with only a few pads, almost always you will have to consider the need for blind or buried vias. So keep in mind that choosing this type of package is going to increase the cost of your board because of the requirement for these additional features that add to the manufacturing time of the board. Okay, like I mentioned, unless it's something very simple, maybe a 16 pad BGA or something like that, you generally are going to have to be very mindful of this and factor that into your design budget. Now, in some cases, you're going to have to use microvias. Now, microvias are a special case of blind vias. In the case of microvias, what ends up happening is that right at the pad itself, a very, very small hole is made in order to drop straight down and be able to go to 1 or 2 layers deep. So with microvias, usually those are also an additional expense because they're not drilled using normal means. Typically they're drilled by a laser. So that setup also incurs a cost. So keep in mind, whenever you're going to be dealing with a BGA package, there's always a possibility of needing blind and buried vias, and sometimes you may even need microvias, which will increase the cost of your board considerably. We're talking maybe a factor of 4 increase in the cost of manufacturing. So you really want to keep that in mind when making your design choices. Now, let's say we have this BGA, this is what we need to use. We're okay with blind and buried vias, we're okay with going with these options. How do we set that up? So as you can see in this board, right now we just have through-hole vias, okay? So in an initial pass, we're going to try to avoid having to go with blind and buried vias. That way we can save money on the manufacturing cost of this board. Okay, but if we did need them, the way we would set that up is by going to the Sizes tab. Okay. Now if you look here at the Sizes tab, you have a minimum drill and you have a minimum microvia. Okay. If the minimum microvia value, if this value is larger than the minimum drill, microvias are disabled. Okay, they're not going to be usable in your design. So in order to use microvias, you have to talk to your manufacturer, you have to know what sizes they need, and you enter that into the minimum microvia setting here. If it's less than the minimum drill, which like I mentioned, because of the special use of the microvia, it will always be usually less. It will always be less than the minimum drill. Then you will enable that feature. Okay, so by default, the minimum microvia is always set to a large value. That way, it's disabled by default. Okay, and in this case, as you can see, we're also trying to get away with not using them because 25 millimeters is obviously much larger than 0.2 millimeters. Okay, but if we would need them, we would look up the manufacturer requirements for this type of setup, and we would enter that value here. Now the blind via ratio, let's talk about the blind via ratio. At this point in time, Eagle doesn't export the stack up as part of your manufacturing data. So it doesn't export the layer thicknesses. So this value at this point in time isn't super critical to get right because Eagle doesn't export that information. However, in the future we will be leveraging that. It's an important parameter when dealing with controlled impedance on boards. So even though at this moment that information is not being actively exported or used in Eagle, in the future it will be. So it pays to be aware of what this is at this point in time. So basically, because of the really small radius that these microvias have, usually it's on the order of 2 mils, 2/1000ths of an inch, there is a ratio that needs to be respected as to how deep that via can go. So as you can see here, we have a ratio between the thickness of that layer and the diameter of the microvia. So as you can see, you generally want this thickness to be much smaller than the diameter of the microvia. Okay, so if we look here, if the minimum blind via ratio is 0.5, okay, that means we're looking to have the diameter be twice as big, at least, when compared to the thickness of the layer. Okay, so whatever thickness this layer is, if the board house has a minimum blind via ratio of 0.5, this diameter needs to be at least twice that thickness. Okay? Usually the manufacturer will give you the important information that you need to have. And you want to have good communication, especially when making something like a BGA board. So in this case, we're going to go ahead and try to see if we can fan it out without having to resort to using microvias or blind and buried vias. If we can, we're really going to save a lot of money in the production of this board. So, like I mentioned, Fanout is a very deep subject. Doing it manually, while possible, is very time consuming. There are a few simple algorithms that are easy for us to follow and be able to do manually. So before we do that, and before we have anybody go and spend hours trying to manually fan out, let's use Eagle's BGA router. Okay, and we can access it in two ways. We can click on this icon here, or in the command line you can type auto BGA. Okay, it's going to bring up this dialog. Now Eagle recognizes components that are set up as BGAs. So what it'll do is it'll show you all of the integrated circuits you have in your design or things that might be BGAs, and then you can move them over to the right side. Okay, so as you can see, I've already moved BGA over to the right side. We can choose to edit the nets that are connected to it. So if I expand this dialog, let's go ahead and expand it. Okay, you'll see that there's a list of every single net that's connected to the BGA. Okay, you'll also see that it gives you the number of contact points that use that net. Okay, and it also tells you what layers these nets are using. So as you can see here, all of these vias are meant to go through the whole board. Okay, from 1 to 16, and to only route any of the fan out signals on those layers 1 and 16. Okay, now normally you could pick a signal and hit edit. Right now that feature is under a little bit of has a little bit of an issue, but I'm going to go ahead and show you what the end result of that is. So for now, I'm going to go ahead and cancel out of this, and I just want to make a note here. You see you have Microvias enabled. You can also control whether they're used or not by checking that box. So let's go ahead and cancel for 1 second, and I want to show you guys something. So if we click on the attributes command and we click here, you'll notice that this BGA already has an attribute called BGA set up for it, and in this case it has layers 2 and 15 in parentheses. Okay, if we go to the documentation, what this basically tells the BGA Autorouter is that layers 2 and 15 cannot be used for routing. Okay, and there's actually a lot that you can control through the attributes in order to define how the BGA should be routed. So let's just take a quick little look. I just want to show you guys very quickly some of the options. Type in BGA, it'll go to auto, we go all the way to the bottom. Okay, and what you can do is you're going to have an attribute called BGA, and then you can add these values. Okay, there's a nets value, which allows you to specify which nets need to be fanned out. So you can select to only fan out certain nets. You can do an inverse of that operation, so you can say fan out everything except these nets as indicated here. You can control what signals are routed on what layers. So in this example, you see that we have layers in parentheses 2 ground. So that means that the ground signal should only go to layer 2. And then here, parentheses 3 with these power signals indicate that it should only go to layer 3. For signal integrity purposes, it really helps if you have them near, if you have the power rails kind of on subsequent layers. But that's a topic for another webinar. The other thing I want to show here is that you can also create an attribute called, you can add to this value and call it Microvias off. Now in that GUI that I showed you before, all of this is set up automatically for you. But like I mentioned, we're having a small issue with that dialog. So if ever that should happen, you always have this as a fallback. You can always go through this attribute manual writing method to activate the feature and to really control how the BGA gets fanned out. Okay, so we already know that from the attributes we saw, layers 2 and 15 are not going to be used. It's only going to try to fan out on layers 1 and 16, and any vias that are placed are going to be through-hole vias that go through the whole board, not microvias, because we're trying to see if we can get that to fan out. So we'll say OK. We click here. We don't need to edit it. We can just say OK to start the process. Now if you look, you're going to see that there's a progress bar down here on the bottom right. Okay, and that gives you an idea of the progress of the fan out. So right now it's calculating. It's doing its magic. And there we are. Okay. Now if we look carefully, we're going to see that the Fanout router respects all the DRC rules. So there is enough room between the BGA pads to allow for a normal via to be dropped. Okay, a normal via. Notice there's no micro via. There's no via that's being dropped within these pads. Okay, they're all dog boning. So the term dog bone basically comes from the appearance that you get if you look at the via, and if you look at the pad, you see there's a little line connecting it. And for some people, that looks like a dog bone. Okay, and that's where the term comes from. And this is a very desirable fan out because, one, it's low cost. We're not leveraging blind or buried vias. And two, as you can see, all of the signals we wanted have been fanned out. Any balls that are on the outside edge don't need to be fanned out because they're easily reachable. As you can see, we can just route straight to them. As you can see, as you go deeper into the BGA, now we have other techniques for fanning them out. So you can see we have this here coming out. Then we have using the bottom layer to fan out. And there's even interconnections between some of the balls in order to be able to fan out those signals. So we see that especially here in the 3.3 volt rail. We see that it connected several of these pads in order to get the result. Okay, so at this point, now that you have the BGA fanned out, it would be much easier to be able to route to all the signals that we need to route to. Okay, so we could use something like the route command and just start routing to the appropriate locations. Okay, so you see that one goes off into space in that direction. Okay. Not being too careful right now. Okay, but you get the idea. By having the BGA fanned out, now it's very easy to route to all the signals that we need to connect to. Okay, and that's the goal of the BGA router. Now, a couple of things to keep in mind with the BGA router. Okay, like I mentioned, the algorithms involved for fan out can be quite complex. It can be computationally very intensive. So depending on your specific BGA, this could take a while. It might not necessarily be as fast as the process I went through now. So don't be surprised if you have a really big BGA and it seems to be taking forever to fan out. That could happen. Okay, just because of memory requirements. And again, the algorithms involved can be very computationally expensive. Okay. Other key points to remember, like I showed you with the attribute information, you have a lot of control. You can specify what layers are fanned out, if microvias are going to be used. You can specify the exact signals and what layer you want them to go to. So there's a lot of control over this and a lot of room to experiment with the fan out procedure. Now if you see that you don't get any result then that may imply that you need more layers, or you may have to try to set up a blind via or a buried via. Again, start with a simpler configuration since that will be the most economically feasible. And then if you see that it fails to get you a full fan out, or a fan out of all the signals you need to have fanned out, then you start bumping up the complexity of the board construction. Maybe add a few layers. If that doesn't work, then you can try setting up blind or buried vias. Okay, so that's the basic overview of the operation of the BGA Fanout router, as well as how to set up blind and buried vias in the DRC. Okay, so before we conclude, actually, because I just realized I did not show you guys the setup for the blind and buried vias. If we go to layers, if you notice we have through hole, it goes from layer 1 to layer 16. If we wanted a buried via, very easily we can just close 2n15 in parentheses, and that will give us a buried via. As you can see, it doesn't exit out the top surface or the bottom surface. And if we want blind vias, then those are set up using square brackets on either side. Let's say we want to go from the bottom up to layer 2. What we would do is on the right side of this little setup equation, we would put colon number 2. And as you can see, it goes up to layer 2. The right side always goes from the bottom up to whatever layer you define there. Okay, so we're going from layer 16 up to layer 2. You guys have probably guessed that on the left side, it's going from the top to whatever layer I define there. So I could do layer 15 colon. And now we'll see that we have from the top to layer 15. So those are your blinds. And then you can do a buried using parentheses. And that's well described here in this little example. But if you want more options, you can always go to the Eagle control panel. Oops, let me cancel out of this first. The Eagle control panel. Under documentation, you'll find layer setup design rules, and there's a lot of example setups there. Okay. So, are there any questions, Ed? What do we got?
That was good stuff, George. Thank you very much. So yeah, we do actually have one question, Jorge. Travis is asking us if there are improvements coming for control impedance. Is there a repositionable grid option coming? In other words, is there a way of setting up a grid for the BGA he's mentioning?
Is that, yeah, redefining the grid relative to the BGA part? I don't know. I don't know, to be honest, if that's what's going to come. I do know that as far as the routing, some of the routing improvements that are coming do involve being able to do controlled impedance. Now, controlled impedance, if we really think about it, in order to have controlled impedance, what you need is whatever transmission line architecture you're using, be it a microstrip, a strip line, what you're looking for is that the cross-section is uniform. As long as you have a uniform cross-section, then you technically have a well-defined impedance. Okay, so from that perspective, we're already kind of talking in terms of controlled impedance. By default, if you're not switching your trace widths part way through a routing operation, then you can say that that whole trace is a controlled impedance in the sense that it is a consistent impedance. Okay? Now, when most people talk about controlled impedance, they want to specify what that impedance is going to be. So in that case, you would calculate the width based on your dielectric thickness to the return path. So in the case of 50 ohms, which is what most people usually want to do for a controlled impedance, you're basically trying to have a width that's twice the separation between your signal trace and the return path. So all of that to basically say that I don't know if we're going to have a repositionable grid option at this point in time. But it may be something that would come. What's your use case, Travis? What are you looking for as far as the repositionable grid? What are you trying to achieve with that? I think that may be a better question. Yeah, the dielectric constant depends on the material. Assuming FR4, it would be 4.
Correct. Yeah, exactly.
It would be 4, but it does depend on the material, correct.
Yeah, well, he's there. So just remember that in this instance, we went basically with a two-layer kind of a setup or four-layer setup, but we didn't really set up just because of for time constraint purposes. But it is possible to configure it per signal if you want to use blind and buried vias as well as microvias. We most probably will do a demonstration. Actually, we'll do a video in that aspect because we'll be able to edit and remove the whole timeline that happens when you're using micro vias as well as blind and buried via setup for BGA fan out routing. So we'll having some videos set up for that as well. Now this document that Jorge has demonstrated here, I've actually used it quite a bit. I keep it a link on my desktop. That way I could do different setups depending on what the users are wanting to do. So if they're working on a 16 layer board, on an 8 layer board, gives me somewhat of an idea if I want to have transitions. So instead of having to figure it out, which actually is not very difficult to figure out under your DRC layer setup, but if you could come here and you see something already being done, remember that the plus sign as well as the asterisk is depending of the pre-prego core material that you're going to be using. So this is a good demo. It worked out really well. Give us a nice clean two-layer section.
Mm-hmm.
If there's any other questions that anybody has that would like us to address.
So I wanted to answer Travis's question because he gave me the situation. If the package is made according to normal conventions, because BGAs are a grid, they have a very consistent pitch spacing. Normally, the center of the BGA will either lie on grid based on the pitch or at a half pitch location. So in that situation, what's probably the best thing to do to simplify routing is you can set up the alternate grid, to match that pitch or half pitch, and that would generate the same effect as a repositionable grid. So I think that would be the way to go right now for handling the manual routing of.
If you have Eagle fired up, Jorge, could you bring it up on the screen and show them where the alt grid is set
Sure.
up on the screen, please?
Sure. So let's
Just in case somebody's kind of new to Eagle, that way they know where the alt grid is set
let's
up.
go ahead and show that. So let me go ahead and turn on the grid so that it's visible. Okay, on. And let's put, I don't know what the pin pitch of this part is.
There's the alt grid right there on the grid settings you have there. It's that second field there you see, gentlemen.
Yeah, it is that one, but I want to see if I can set it up to match what this is. That way.
Oh, the pitch that you have currently on this
Yeah, yeah, that's what I want to try to do. Let me see if I try 0.8. There's no way I could be that lucky to get it on. Okay, let me try something. You do a group. Let me actually do a Control Z on this.
How about just moving it and hit the control button the way it snaps?
Well, what I wanted to do is select it and then use alignment to put it on grid.
Okay, there you go.
So, okay, perfect. I had it. It's 0.8. So what you
Yeah, it's perfect in the center.
So what you would do then is you would set the alt grid to be, something like a half of that, so 0.4, and then you would pretty much line up perfectly. So I would go here, I'll set the alt grid to be 0.4, and then when I want to route, I can just use that for locating the points. So that was a fluke. I did not know beforehand that it was a 0.8 millimeter pitch on these, but it is. So I am really happy.
Well, that highlighted one of the other features, which is the alignment feature, which is pretty cool. So just for those that did not know that this latest version of Eagle does have the alignment tool embedded in it. So it's meant to do groups, or you could do it for single elements as well. So that's pretty neat. Snap them on grid. Okay, so I think we've answered all the questions. as a summary, we used to give you an idea how to run with the DRC and take care of your layer setup. The documentation is located in your Eagle Docs folder. You can access the documentation from within the Eagle control panel. The Eagle control panel, you're going to see multiple trees. One of the trees is called documentation. There you're going to see if you'll be able to find the manual as well, the tutorial, as well as a document in regards of how to different setup examples for blind and buried vias as well. In regards to the BGA Fanout, the BGA Fanout is a great tool. It's going to be on the left-hand side of the toolbar towards the bottom. Looks like a BGA. The BGA Fanout does allow you to do respective modifications per signal. As Jorge indicated earlier, you'll see the list of all the signals. Once you see all those signals, per each signal, you could set up how deep layers you want it to go. So a signal could go down as one layer. A different signal could go down as much as 3 layers. So you could set up the signals per. I'm sorry. You could set up the depth of per each signal. So on complex, if you have something that is very specific, or you want to take advantage, if you're using ground planes or power planes, that's where you're going to be taking advantage of this. BJ Fanout is quite complex. This makes it a lot easier. This takes care of a lot of um, um, effort by the engineer, and kind of like automates it. Now, if you automation will work if the setup is done properly. So, thank you thank you very much everybody for joining us. Towards the end of this month, we'll be having talking with a pro with a panelist. We'll send out notifications to